Hello everyone and welcome to lecture 2. This time around we're going to be talking about some of the basic concepts that have to do with printing. We're going to look at the halftone pattern and a little bit of how that works to let us reproduce images in color. So I guess I could make that singular, just say the fundamental of print, but the basic idea is that we're going to be making an image using a series of dots. The reason for this is that the printing process is a mechanical process. It's not an analog thing like what we do with the pencil when we're shading in a drawing, where we can apply more or less pressure to adjust the tone. The only way to adjust the tone in your printed image is by adjusting the size of the dots in that pattern. So the reading assignment this week gets into this a lot more. I'm going to hit you guys with a really short lecture this time around again, and not repeat the same things over and over again, hopefully. So definitely get in and pay attention to the reading there. It's going to cover it in more depth than I am today, but I just want to show you a couple of things as a supplement to the reading there. So if you haven't figured it out, or you haven't looked at the reading yet or whatever, this is kind of what a halftone pattern looks like. There's some different types of them here, but what we're looking at on the screen right now is a variation between light and dark. On the right hand side, that's kind of what it would look like if you're looking at a black area of fill, or maybe what you'd see where there's some shadows in a photo or something. Again, this is on a printed page. On the left hand side, that's what you'd see in a light gray area. Notice that the dots are never gray in any of these cases, and the paper is always white underneath it. You only have two options when you're talking about tones and shading in a printed document. You have black and white. We'll add color into this a little bit later, but that gets a little bit more complicated. The idea here is that if we want it to look gray, we just use smaller dots of, again, the same exact black as we're using when we're printing solid black. So we're not printing any other shade of gray. There's not 255 levels or anything like that, like you'd get in a digital file. But we are able to reproduce gray, obviously, in a printed document. If you look right in the middle there, where it's the squares of black and white at the very center tile, that would be about 50% gray when you zoom out far enough to look at that. Those squares, and this isn't exactly representative of what would go on a paper, but it would work. Because there's half white and half black on the page, you zoom out far enough to where your eyes can't resolve the detail, then all you're going to see is the combination of the two. So that's the basis of how the halftone pattern works. Definitely do the reading and gets into it more than what I did just now, but that's the idea. The book also is going to talk about halftone screen, and I just wanted to point out what that is. Some of you may be familiar with photographic processes like developing film and printing on film. If you are, then this will make sense to you, hopefully. At this point, few people probably have a lot of experience with traditional printing in an old school print shop like I did back in the day. But when we talk about halftone screen, this is like a lot of things in the design world. The terminology comes from older processes. So at one point, in order to create that series of dots that go on the paper and break that image up from a continuously toned image to a halftone pattern, you had to use a screen. The way that was done is you put a sheet of glass over your document that you want to reproduce in print, and that sheet of glass was etched with a fine pattern of lines, a screen. And then that document was exposed onto photographic paper or a plate most times, using light and photographically sensitive materials, just like if you're developing and printing film back in the darkroom in the day. If you don't understand how that worked back in the day, which I wouldn't blame you if you don't, that may not make a whole lot of sense, but if you do, if you are familiar with that process at all, then that's what happened. It was a photographic process, but you had to make these tiny little dots in order to be able to reproduce it mechanically with some of the processes that we're going to talk about a little bit later. So that's what it was. It was literally a screen that was placed over the image to expose it photographically on a plate. That may sound like gibberish now. It'll make a lot more sense as we go along. Don't worry, but when you hear about screening, that's basically what it was, is you're converting an image, a photograph, design, a drawing, something into a series of dots. And that process still takes place. It's done digitally now. It's done with a computer in a RIP, which we're going to get to. And you'll see that in your reading too. Um, Resolution. Now, we're going to talk about resolution a lot more in a later chapter, so don't worry too much about it right now. Many of you are probably familiar with resolution in terms of dots per inch or pixels per inch in digital files. You have cameras or even cell phones with cameras that you know how many megapixels that is, and that relates to how many dots or pixels are in a certain area. So it's referring to density of information in a certain space. Printing is similar. It's the density of information in a certain space, but it's measured a little bit differently. So on a paper, we're talking about lines per inch. The reading will go into this a little bit more, but the printed quality is going to be affected greatly by how many lines per inch you can use. We'll look at how to calculate lines per inch in Photoshop and some other things down the road too. But just something to start thinking about is that lines per inch is the measurement of resolution when we're talking about print. Okay, now here's what I really wanted to get into with you guys. This, like some other things, we're going to come back around to and dive in a lot deeper in a later section. But for now, I just wanted to introduce the concept to those of you who may not be familiar with it. Basically, all the colors that we see on our monitors are composed of just three primary colors: red, green, and blue. When you mix red and green together, you get yellow. When you mix green and blue together, you get cyan. When you mix red and blue together, you get magenta. You'll notice that matches the names of the colors on the second bullet point there. Same thing, if you mix cyan and magenta, you get the others, and on and on and on. If you look at a color wheel, just Google image search color wheel and you'll get a picture of it if you don't have one available. But take a look at that and see that as you move around that color wheel, those are the colors that you transition from. Red to yellow to green to cyan to blue to magenta, back to red again. And it goes around and around and around. The image that you see on the left, that little GIF, is just showing the effect of those colors as they blend together. This is an additive color system that you're seeing on the screen though, and we're going to talk about what that means here on the next slide. So on the right-hand side, you see red, green, and blue. When they mix together, makes white. On the other side, left-hand side, you have cyan, yellow, and magenta, and when they mix together, it makes black. And this may not make sense just looking at it initially on the screen, but I want to dig into that a little bit deeper. So if you think back to the days when you were in grade school or kindergarten or whatever, and you were finger painting in class, and you mix together all the finger paints or watercolors or whatever, oil paints, whatever it is, the more different colors you mix together, do you get something bright and vibrant? Not usually, no. The reason for that is when we're working with physical pigments and dyes and things like that, it's subtractive color, meaning that light from the sun or the lights in your room or the fluorescence in the classroom or wherever it is are hitting that material, and some of that energy is being absorbed by the material due to its physical properties. Certain wavelengths are absorbed and certain wavelengths of light are reflected off. And depending on which ones are reflected off of those materials because of its physical properties, those are the ones that hit our retinas, and that's what we see. So when we talk about subtractive color, we're talking about color in the physical world that is absorbed into certain materials. And then whatever's bouncing off of that or reflecting, that reflected light is what we perceive. And so when we see things, the more light is being absorbed into something, the darker it gets. So think of a black piece of paper or paper with black ink on it, and it's just absorbing a whole lot more light, right? If you go out here in Arizona in the parking lot in the summertime and stand next to a black car and bump up against it with your arm, it's going to be really, really hot. A white car is going to be hot here in Arizona too, but you guys can hopefully imagine it's not quite as hot. And there's a reason for that, is because the color black is absorbing a whole lot more light. So the physical properties of that material are such that it absorbs more light, and that light is again translated into heat, which is why we're talking about that. But in print, that's what's happening. We're putting down ink or dyes on a material, on a substrate, and certain properties of those dyes or inks or pigments are absorbing certain wavelengths of light. That's all it is. Now on the right-hand side, RGB, this is additive color, which means that the more light we add, the brighter it gets. This applies to things like electronic devices, your phone, your computer monitor, your TV, Whatever it is, if it's electronic and it's projecting or displaying an image, it's using additive color or emissive color. It's emitting light rather than subtracting or reflecting it. So RGB, when we mix those together, we have our computer monitor. If you were to take a magnifying glass or a microscope or something and looking really close at your computer monitor, you would see that it's made up of a whole bunch of red, green, and blue pixels. When they're packed in really tight and really close together, you will see that you can make out a color. So looking at the screen right now in the video that you guys are watching, those red up there in the red circle that's just a whole bunch of red pixels being activated in the monitor. And if you zoomed in with a magnifying glass there again, you would see that the red pixels are on and the green and blue ones are not on, or not on very much. Down in the blue area, same thing. The blue ones are on, the red and the green are not. In the white area, you would look at and zoom in and you would see that actually red, green, and blue are all on full brightness. So it's interesting. I will show you on the next slide, or a couple slides from here, a little video animation of a halftone screen. But there are tons of images out there too for monitors. We're not talking too much about monitors now, but I just wanted to pull these up for comparison. One last thing before I move on is if you'll notice that the areas on either of these where yellow and cyan overlap, for example, it's green. Where magenta and yellow overlap, it's red. And this works both cases in additive or subtractive color, that these are colors that kind of cycle between each other. All right, so now talking a little bit more about printed color. If you look here at the image, the way that we print is not mixing paints like we did back when we were doing finger painting in kindergarten. We don't mix inks to create specific colors in printed documents. Instead, we make tiny little dots of distinct colors like cyan, magenta, and yellow. And when they're small enough and close enough together, our eyes and our brains can't distinguish between them. And so what we see is the blend of the light that's being reflected off of that color. So I'll show you again. Like I said, I have an animation that shows this a little later on, but here's an example of those three colors. On the top, cyan, magenta, and yellow overlap to make the image in the bottom left-hand side. Then we add to this, when we're printing, we add black ink as well. Because like I said before, if you mix together all those colors, typically you didn't get pure black. It was very difficult to get pure black mixing a bunch of colors together of paint. But in order to get a sharp image with lots of contrast that looks good, in printing we need to add black as well to that halftone pattern. And so you see on the bottom right-hand side, there is more contrast in that because we've added a layer of black ink as well to sharpen that up. Okay, so if you look at this, you'll see that there are a whole bunch of distinct dots. And if you were to zoom in even closer, you would see that there's not green. Look at the top left-hand side of that. At least to me, it looks like there's a bunch of green. And that's just because those colors are really close together and starting to overlap a little bit. But they're really not mixed together. There are distinct cyan, magenta, yellow, and black dots of ink on this paper. Now, when I hit play on this and zoom out, you can see it resolves into an image. And if you're able to get a hold of any kind of printed material and zoom in on that with some kind of device, you would see the exact same effect. It's difficult to create a video like this where you zoom in from that high of magnification, but if you guys are able to see something like this, get a hold of any kind of print, and you have any sort of magnification device, a magnifying glass up to a microscope, whatever it is, if you're able to do that with a macro lens on your camera, fantastic. Take a look at those. I'll post some other pictures down the road too and give you some more examples of this, but everything that's printed out there is done kind of the exact same way. It's far more economical to print with 4 distinct colors that we can just create the illusion of a whole lot of other visible colors in the spectrum that we can see. So that's it. Make sure you let me know if you have any questions. We have a lot of work to do this week and a lot of reading, so have fun.